So let me introduce Ivo, who is the chair of CCP4 and is going to tell us all about it.
Yes, 1979, little did we know. Now, this is a picture comes back later and shows the power of graphics. And we think of graphics card today as something different. But I want to start, and I want to cover three things or four things really. The history of what we did in CCP4. I've been sort of since my early years of my career, I've been working with CCP4. We have a mixed economy of funding. So funding streams are coming from both academia, and that is research councils, as well as industry. This is one reason why I think CCPs matter, because we can attract that funding and bundle it. And I would, at the end, give an outlook to see how CCPs could communicate and work together, where I see a strength. So we are coming from the field of diffraction. This is all stuff that you know, and the MRC here. So whom do I tell this to? So we came from diffraction, from scattering experiment, from fiber diffraction, and we stand on the shoulders of giants here. Crystallography goes back much longer, namely to the 19th century, and has gone a couple of really hallmark discoveries that paved the way into the modern crystallography. And so we've been, I've always, used this type of device. So before cryo, now we're using freeze everything down. But recently we started to use room temperature again, because this is where biology happens, and that's what we want to be doing. So here are those structures that are really sort of, really gave the understanding for how structures work, and how we think biology is encoded in proteins. And so John Kendra and Max Perez. Here is the theory behind it. And for me as a German, it was always nice to come to the UK, because it's the country of crystallography. We have some in Germany, but the UK was leading the way. Macromolecular also had its milestones in really determining structures, but also in methods development, and that is the engineering that's behind it. This is Ken Holmes, is my PhD supervisor in Heidelberg, building in what we call Bunker 2 in Hamburg, the first X-ray station at the synchrotron. We had Doomsbury as we call it, and then we have Diamond. And now the Diamond light source is really a powerhouse of science. The upgrades programs are happening around the world. This is particularly important for imaging, less so for diffraction. And shameful to say that Diamond 2 is only coming online in 2029, so we're 10 years after the others. That to me is a bit of a problem, but I think it still goes ahead, despite all financial pressure. So that's good. Whether it's going to be in UVK exfil, I don't know. The massive investment, and whether we need that is questionable. We started in 1979. And so in the beginning, it was a couple of academics writing software. That's not a good start, you realize. It's all cross different ideas, things that one needed, and we wanted to put that together. That was in the 1979, where people then thought this could be a computing project. It was CERC funded and later BBSRC funded. And so that's where the initial driver came from, putting something together that could be funded by the research councils. Now, you always have to distinguish between infrastructure and scientific computing. And this was a science-driven project. Now we're going a little bit later, or shall we point out other drivers? Other drivers, I'm showing you now one, is data and how you would program. You would program these days on cards. So this is how you programmed things. And then you would save things to a floppy disk or to larger disks. Do you want to see how a 10 megabyte drive looks like? It's this size, right? So data technologies are a driver. And with that, I'm posing a question here, and that is data storage. Do we necessarily need to store all data? So FAIR principles is certainly something that is very dear to us and we need to adhere to. Do we store all data? So that has two aspects. One is the metadata that is normally lost, but the other is data collection goes extremely fast these days. And if we store everything we have, we need to think about even putting the computer very close to the detector to be able to transport the data, then the data management. And it reminds me of this problem. You know, our genome accumulates data. Is it really all useful? We don't know. The answer is we don't know, but we have AI to look at these problems and even get something, you know, go through the mist and the haze and see some information in the noise. It'd be interesting to make that decision. For some of the things like we do in crystallography, we have no hits, and then we can easily discard those images. But other images, do we want to take everything that we collect? It's a really big problem, I think. And then we have the computer technology. That's ever since improved. And so I remember there's still the DECVAX computer that we had in Hamburg. This is when I started my PhD, and then Evans and Sutherland would sit in the corner. This is the equivalent of a house that you could buy times, well, 15K versus, you know, 200K for a VAX. And graphics. Graphics was an enormous breakthrough to have the ability to have a graphics workstations. That's the workstation, size of the workstation, to start doing these kind of things. So where do I see problems and where do I see challenges for CCPs, and where should we go? One of the things is I started telling you the story by saying a few scientists got together and wrote their individual softwares. The ethos of CCP4 is we take all. And we have multiple solutions for a number of different problems. Molecular replacement, one of the common problems. There's a molecule, put it in my crystal structure, has various different programs, various different softwares, and you can use all of them. So should you exclude software? Should you allow all software into your suite? Is a big question. We always had the feeling it is open, and we need to have access for all of the different solutions that we have, because maybe one solution can do better than another. The technologies, I've told you about data, I told you about computing, those are all emerging. Then is the facilities, your microscopes, our X-ray facilities. They actually show where the field is going. We didn't know when we had the EBS upgrade at ESRF whether we could use X-rays at that frequency, at that speed. We now do. And now we do new experiments, novel experiments we had thought about. Namely, we do time-resolved crystallography. So we didn't think we could do this, and we didn't actually really foresee that. We just thought, you know, things get faster, but we couldn't see the experiment. So technology drivers are very important in science. And then we need to have a structure to be able to distribute our software. And that is a challenge for each CCP, because you want to sort of give it to the users. And then user support and education, you've already touched on these issues, but there is a new issue. And that is that people sometimes they will start using your software as black box, and then they have no clue what they're doing. So you need to educate people really how to use things. And now we have computed structures, AI-generated structures, no longer crystallographic structures. Crystallographic is the database, but then AI on top makes predictions of how structures look like. But the people have never seen an experiment. So you need to tell them what the experimental part is and what that has. So support and education goes to more than teaching people your software. It's to understand what the data entail. And this is really just a highlight of what kind of advances we've seen. We've seen structured genomics. You had genes, human genome. You wanted to know and understand the function of all proteins. Okay, so that's one thing that happened. It's actually led to a process of industrialization where we have machines that actually help us in these pipelines. We have advances in the synchrotron sciences. The synchrotron sciences are really sort of a lot of a big driver to do this. Technologies for detectors. We've seen that the explosion of the EM field is really detector technologies, is being able to collect those data. Algorithms, new ways of computing things, pipelines, automation, DAO, AI, all of these are challenges, but also opportunities. And then the numbers of structural biologists. Now, for us, for CCP4, there was a crystallographer at the former time who then worked on one protein for an eternity of time. This is no longer. And now we look at a problem, a biological problem, and we just say, you know, this is a question, this is the technique I would be using. And I would be using EM, I would be using cryo-EM, crystallography, tomography, what have you. And we are not living here in the CCPs in isolation. I know we have to have individual CCPs, but I really pledge for doing a collaborative spirit, because that's how the researchers go at these things, go with their scientific problems. Structure-based drug design is something which happens in academia, which happens in industry, and crystallography has a huge value in delivering the precision of the data that you need for this. And the pipelining is one way of achieving this. It's making it very easy for anyone to just put this thing up. I mean, it costs a little bit of money, but then everything runs like a black box and machine, and you get everything out of it. But this picture also shows you not just data collection in the X-ray side, which we are serving the community with the CCP4 software, but it's also all these other experiments that you see here, robotics and so forth. And the question would really be, how do we work with these kind of things, integrate data, include metadata? Funding is a mixed economy for us, and we have a number of different things. We have science, we have pharma, all of them using the software, automated pipelines, and the software is funded both through academic use of software and BBSRC funding, as well as the income, which exceeds the BBSRC funding by far and allows us to have about 30 different positions funded by this industrial income. We have to do this because we want to have builds, regular builds of the software that we farm out to the sites, and it's about 20,000 license give out, academic licenses. We have about 200 industrial users. There's a structure to it. We can discuss this later, how we shape this and how we get the community to work with us, working groups and work packages across a grant. And this is the current grant, and we are in the middle of that. Now we're thinking of the next funding period. We're thinking about things like ED&I. We're thinking about how we make it more open and fair, and how we review. This was the last grant in 23, and now the next one is coming up in 28. So you're always thinking about the next round of funding. Yes. Why I think CCPs matter is another thing that is kind of interesting. So we now teach how to look at software structures with the software. We now teach how to analyze data, and that encompasses, as I say, the AI-built models. We have a lot of meetings like you guys, where we speak to the community, do this teaching and training exercises. We get information and input from the user base. And we have different ways of communicating to the user base. And we integrate these computed models into our pipelines, and that's a very important step that we do. So the synergies exist with in a number of different ways. Speed of the structure determination helps us really to look at these things and look at models. We have electron links with electron microscopy, which is on par. This all gives different information, puts things together. AI are tools we use, and the EM is highly complementary to what we're doing. And in the future, I think crystallography is important in both academia and industry. It delivers the last precision on the structure that you require to do drug design. But that's not all there is. So we are now trying to think about how we continue with this funding cycle and how we do. And funding is always a driver for these big CCPs, I know, and it's always a headache on how to do this and how to obtain the funding from the research council. So these are kind of things that we are currently seeing. Right, we are thinking of opportunities, and these are my last slides, but it's a couple of them, where I'm thinking what is actually the kind of projects that we would have. And we were looking at building a cross-CCP network, which we call DREAM. Okay, and we look at collaborations between different CCPs. And you've seen this list, but there are a couple in life sciences that are part of this now. The idea here being that, you know, if you invent a thing once, maybe you want to have a code base and data exchange very much, and make that easier between the different CCPs. That's what we're trying. Here are my 4 science cases from my own work. First is, for example, enzymology. And here we look at the catalytic cycle. What I know see as an interesting thing is to put quantum chemical calculations on these kind of things, do that. And this we call a quantum crystallography. That's just one of the developments we have. I'm quite interested. This is a recent one we've done where we looked at classic diffraction, neutron diffraction, where we can see the hydrogens, and then actually a pump prime experiment at an X-ray laser source where you would have a change in structure, you have time resolution, where an arginine moves in and out. What it means is the thing is that you can now do time resolved work. Or you look at antibodies, we have crystals of one antibody, crystal of another antibody. They look identical in terms of the structure. These are the two arms of the antibody. And they have a little bit of a difference here in the middle in the disulfide bonding pattern, but one is active and the other one is not active in cancer therapies. How would you know? And we can only know by doing scattering and then molecular dynamics calculations. So we need more than one CCP to solve that problem. And here is what I have in my lectures for the students, and I show muscle, and you see the cycle now of the muscle, and Ken Holmes in Heidelberg did one of the early studies on fiber diffraction. Now we're putting all these things together with EM structures, with crystallographic structures, and we come to these absolutely stunning and beautiful pictures of how muscle now looks like in tomography. And you see how you need all these different methods to start understanding biological systems. So my personal wish list is that we do not have multiple developments. That's one thing to look at. Whether you have software that is already there, you can use it. We use the best of the most powerful of the computing, but also be careful about the results that we're using. And then we advance with the technologies and the techniques that we see in the field. And so what we have done is we founded this dream collaboration. These are the collaborating CCPs, and I take it CCPN is going to say a few words as well. All right, open for questions.